So, we are in the last part of our study of the Karush-Kuntaker conditions. It is not that, or the Fridtjohn conditions, it is not that this is the last part of the subject, but just because of the limited time we have in the course, that we really have to end it here. Tomorrow we will give you a set of exercises on this issue, which I think you should try at home. They are very, very important. Now, some of these exercises would actually be given in a solution when FAQ would be attached to the course at the end. So, that those exercises, some of the exercises which are important would be solved. And today we are going to first show a very important thing, again using the Mochkin's alternative theorem that we had studied in the last lecture. It says that if you have a linear programming problem, all your John multipliers would always be normal. There is no abnormal John multiplier, and it means that the KKT condition always holds. Whenever all the John multipliers are normal, we will call such John conditions as the Karush-Kuntaker condition after the seminal work of Kuhn and Tucker, and later on found to be have also been done by Karush. So, it is in this field of naming, it is very, very strange, because somebody calls it Karush John condition, somebody calls it Carathéodory John condition, somebody calls it John KKT conditions. So, there is a lot of things. So, we will just have John conditions and the Karush-Kuntaker conditions. So, we are here today considering linear optimization problems. When I am considering linear optimization problem, I am considering minimization of a linear function. Any linear function on Rn is given by an inner product subject to so called affine constant, that is linear minus a translator real number. Maybe I should write equal to 0. There is a standard form, and all the xi's are greater than equal to 0. The decision variables. So, here C is an element in Rn, and so is x, then of course, the decision variable. Each of the AI's are in Rn. Now, if I consider now a matrix whose rows are these vectors AI, then I can write down this linear optimization problem in a more compact form, and this is what is called the linear optimization problem in the standard form. So, I will call it LP, that is called, and this is what is the standard form, and this is the form that is used to actually start solving it by using the so called simplex method or any other method. Of course, you could have a more standard form by putting this to be less than equal to 0. This requirement comes largely from practice. It is not really required for mathematicians to think about xi greater than equal to 0, but in practice, in most cases, your decision variables are non-negative integers. It could be say number of vehicles, it could be number of things to sell, it could be number of employees, number of students, blah blah. These decision variables are or amount of food that you buy, the different types of food. These are the types of food, and so you are making a diet plan, and what is the optimal diet plan and all those things. So, linear programming has a huge literature. A substantial amount of linear programming has been done in the course on convex optimization, which I gave earlier. Here we are not going to spend so much time on linear programming, because this course is rather general foundation of optimization. So, we are going to mention this very, very important fact that, so you can write this problem in a slightly compact way. So, if A is a matrix which is formed by taking all the rows as the vectors AI, so it is a row matrix of m rows and n columns. giving you this equation basically x minus b, b is a row vector in a column vector in Rm, and x is also written as greater than equal to 0, and this structure is very important to consider, because here you would observe that this x greater than equal to 0 actually means component wise greater than equal to 0. Now, once I have this, I am now inclined to write down the Fridtjohn conditions. So, the conclusion that we will have is, if x star solves LP, so any solution of this problem, is a global solution, because it is a convex programming problem. Every local minimum is global. That I have also proved in my other course in convex optimization. You see these two courses, convex optimization and this foundation optimization, could be considered as a compact course and a 2-semester course in optimization. So, here if x star is a solution, so this is a major result. So, so this was known to Kuhn and Tucker, this is one of the celebrated results. So, this was known to Kuhn and Tucker. So, okay, I would not put it there like that. I think historically it may not be a correct thing to do, but Kuhn and Tucker of course knew this fact. So, I have written down the result, which will say that if x star is a solution of LP, then all John multipliers at x star are normal. As we will deduce this, you will soon see that there is nothing like fact that the multipliers depend on x star, the solution. The multipliers that will appear, or the John multipliers that will appear, do not depend on x star. So, whatever be your x star, the multiplier set is same. So, now let me just try to prove this fact. So, if you remember what we did when we tried to prove the Fridtjohn conditions, we tried to prove that a certain system of inequalities are basically strictly less than, they are strictly less than 0, then apply the coordinates alternative theorem. Here we would go back trying to apply the Mochkin's theorem that we have learned in the last class. I would like you to have a look at the earlier lecture, the Mochkin's theorem of the alternative, which I do not want to put it here once again, because we have already done just in the class before. So, what I would first prove is the following, that if x star solves LP, there exists D in Rn such that let us see what is happening, such that C of D is strictly less than 0, AID is equal to 0, and EID is less than equal to 0. This is what I am going to prove, where EI is basically if you write all these xi's each x1 as a function of x1, x2, xn, then you can take the gradient of that, and that will be 1 0 0 0 0. So, that is E1. So, where Ei here I should write I equal to 1 to m equal to 1 to, you can put j also if you want, okay, Ej if you, no, let me put I, but that is exactly the thing that I have been putting, does not matter, the index is, you know what, this is the index over this is the index over that. So, I equal to 1 to, okay, I equal to 1 to, what was that, n. That is what we are going to first show. Sorry, I made a mistake, there exists no D in Rn. So, what I am going to show that there cannot be any D in Rn for which this is true. So, this would be the first system of the Gordon's theorem of alternative that we did in the last class. So, once you understand that, you can immediately know what is the final system that we are going to write. So, let us start by proving this fact. So, let us see how we prove this fact. So, suppose on the contrary there exists, I am just taking the mathematician's liberty to write like this, a D in Rn such that there was system which I call sys 1 has a solution. So, now you observe one fact, x star is a solution. So, now I will prove that x star plus lambda d, x star plus lambda d will be for some lambda strictly greater than 0, will be a solution, will be a feasible solution to the original linear programming problem, and it would be a solution whose where the objective value would be strictly lower than the current objective value C of x star, which is the optimal objective value, and that cannot happen. So, it is exactly the same way that we proved there, we will show this. So, let us see how we do it. So, take a D, so take you have this D, construct x star plus lambda d with lambda strictly greater than 0. Then what does this give you? This now this shows you AI sorry, this should be minus here, I made a mistake, because here it would be minus xi less than equal to 0, because we have learnt it when you write this one, you can also write it alternatively as minus xi less than equal to 0. So, you write it in the form of inequality constraints. So, the gradient of this function, so if you write this as g1 x is equal to minus xi, then grad of g1 x is actually minus ei. So, ei's are actually vectors of this form, 1 in the ith place and 0. Now, let us see what happens with this. So, lambda is strictly greater than 0, I will have AI x star plus lambda AI d. Now, AI d is equal to 0, because d is a solution of this system of equations, while AI x star being the solution must be a feasible point that is equal to b. So, it is finally b. Now, how do I know that? Now, x star plus lambda d is also component wise greater than equal to 0. To see this, observe this equation, this would give you minus first one, it will give you minus di d1 greater than less than equal to 0. So, d1 greater than equal to 0, similarly d2 greater than equal to 0. So, basically what this equation gives you is that d is a vector which is component wise greater than equal to 0. Once you have that fact, you can immediately see that x star plus lambda d is also greater than equal to 0 component wise. Now, let us write down, let us put this whole thing here. Now, let us observe what will happen if I compute the objective function at this point x star plus lambda d. Now, the theater would be changed to this point. So, I will just basically use this now. So, this would be equal to C of x star plus lambda times C of d. Now, lambda is strictly greater than 0 and C of d is anyway strictly less than 0 because d is a solution, and C of x star is C of x star. So, this we have added a strictly negative quantity to C of x star, which means what I would get is nothing but a quantity, this quantity which is strictly less than C of x star. So, what it means that x star plus lambda d is a feasible solution at which the function value is strictly less than the optimal function value, and this is something which is impossible. This is an impossibility, contradiction. So, this is what mathematicians, one of the finest tools the mathematicians has is called proof by contradiction. Now, once you have got this fact, so this fact is correct that there if x star solves LP, there exists no d in Rn such that this holds. So, this system does not have a solution, and this system looks like the first system in the Mochkin's theorem of alternative. Once that is done, we will see that we can now write down by applying the Mochkin's theorem of the alternative, the Lagrange multiplier rule or the Karush-Schunter condition, whatever you want to call it, or the Fritz-John condition. Now, I would again now observe this fact that if this is the story that this system does not have a solution, Mochkin's alternative theorem will immediately tell me that there exists scalars lambda naught greater than equal to 0 and lambda naught not equal to 0, which means lambda naught is strictly that is lambda naught strictly greater than 0, lambda I in this particular case element of R I equal to 1 to m and Si element of, because this is a greater than less than equal to 0. So, Si greater than equal to 0, I equal to 1 to n, such that lambda naught times C plus summation lambda I ai times lambda I ai times plus Si minus Ei times this is equal to 0. Now, what I will do in order to get something nicer in the way people write in the actual literature, I will replace lambda I by lambda I will write this as lambda I dash, because lambda I is just a real number. So, I can just write it like this. So, I can basically add to lambda I some number, so that the thing is 0. So, I can write lambda not C AI plus lambda I dash. So, it will become minus lambda I dash. So, SI EI will finally give me the vector S. So, lambda naught C is equal to summation lambda I dash AI plus S I E i's, that will combine to give me the vector S, where S is nothing but S1, S2, Sn, because each E I is 1, 0, 0, 0, 0, 1, all those things. So, this is what I have. So, now I will divide both sides by lambda naught, because lambda naught is strictly greater than 0, to give me C is equal to so I will write this lambda I dash by this as this, and I will write this as S bar as divided by lambda naught. Now, what it is important to note is the following, is that this can be written in a matrix form, because this is nothing but the matrix multiplication, and you should be able to note that C can be written as A transpose lambda bar plus S bar. Now, you observe it very carefully that this C is nothing but the gradient of this objective function, this is gradient of the constants, and okay, these are associated with the gradients of this. But you must be thinking that there is some interesting feature of Fridtjohn condition which is not here. I have not got that, the complementary slackness condition. Now, how do you get that? I guess there are a couple of ways to do that, but I will now tell you one way, and I will leave it to you to find some other way by looking at the affine version of the Mochkin's theorem from Goulet, for those who have access to that book. Now, what is important to know is the following. Here what I really wanted was this greater than equal to 0. Suppose I had xi strictly greater than 0. Right. Then I do not really, so I have xi strictly greater than 0, and what I really want to do is the following. So, xi star, so take any xi star which is strictly bigger than 0. Take d could be a negative number, does not matter. Now I have the controlling capacity on lambda. So, I choose my lambda in such a way, make it so small that I can always have xi star plus lambda d, d could be negative, to be strictly greater than 0, does not matter. does not matter at all. It will always have for lambda sufficiently small. So, by controlling my lambda, I can always make xi star, whenever xi star is strictly greater than 0, it will always imply this by choosing lambda sufficiently small, lambda greater than 0. Now, observe that if xi star is equal to 0, then I cannot do anything, because if delta is d is negative, then okay, this will be negative only, d is less than equal to that. So, d, all the components of d is negative, then this would be strictly less than 0. So, that will not be what we want. So, what we really need to look at are those points of x1, x2, xn star, x1 star, x2 star, x3 star, x4 star, that x star vector, which are the components which are 0, that are the point where we really should concentrate, and that leads us to consider what is called the active set index, which we have already done in the last class also. So, consider all those I from 1 to n such that xi star is equal to 0. So, d corresponding to those xi stars must be greater than equal to 0. So, this would lead us, because we are missing the complementary slackness condition and we are trying to push in that those things there. Also you could have taken here to be put one xi or something like that, that is a different issue. So, now what I want to now tell you is that this is not exactly mimicking the way we proved the Fridtjohn condition, this is not the exact one. So, what I am trying to tell you is that now let us see, we have concluded conclusively that d is greater than equal to 0 is required only when the case xi star is equal to 0. When xi star is strictly greater than 0, I have no problems. So, what I am now doing is I am now looking at this system. So, the same story, I am now going to write it in a much more compact way, because you are now much more. Now, I would only consider ei d to be less than equal to 0, sorry minus, for all I in the active index set. Now, if I do that, I can actually prove this fact. So, I can prove that this system, which I can call as sys 1 star, this system has no solution. This has absolutely no solution. I would leave that as an exercise to you. Please consider this as your homework, HW. Now, this system does not have a solution, so I can go back and make my changes here. So, I will apply the same Mochkin's alternative theorem that we learnt yesterday, but I will put this. So, basically what I will have now here is summation I is belonging to Ix star. Now, what I do Si bar, now we can write now for I not in Ix star, take Si bar equal to 0 and construct sorry SI bar minus EI. Take that to be 0 and construct the vector S star, which is, so S star in such a way star such that S star I is equal to S I bar if I is in I x bar x star sorry, and is 0 if I is not in I x star. So, in that way if I now compactify what I have done here, so I can write this as lambda naught can be again in the same way. I can now write this whole thing as a vector S star. So, I can now compactly write this as A is equal to C is equal to A transpose lambda bar plus S star. Now, look at the nature of Si star. So, whenever I is element of Ix bar, Xi star is equal to 0. So, Xi star into Si star would be equal to 0. Okay. Xi star into Si bar, which is same as Si star, would be 0. Now, when I is not equal to Ix bar, Xi is strictly bigger than 0, but Si star is equal to 0. So, which means that finally I get what would you and I call the complementary slackness condition, which says this is equal to 0, and this is essentially the two major lines of the John conditions. And you see that lambda naught, whatever way you get, this is the only way to get the multiplier rule by applying the separation theorem, which is the Motzkin's theorem. So, here I had forgotten to write, so I have told repeatedly, but just for your memory I am just writing it at the last point. Apply Motzkin theorem, Motzkin's theorem of alternative of ALT, shortcut anyway. So, this is, of course, people would like to extend it like this, writing Ax equal to B, Ax star equal to B, which is of course anyway has to be true, because if X star is a solution. So, this is the essential system that you have to solve to find out X star. So, this is usually called this, though this is the John multiplier, Fritz-John multiplier rule that we have got. You see the multiplier associated with the objective function of the gradient is always 1 or positive, which means this always, you cannot get it otherwise. This is what we call the Karush-Kuntakar conditions. So, we have learnt a very important aspect of optimization today, the Karush-Kuntakar conditions or KKT condition associated with a linear programming problem, which is essentially this fact that if X star is a solution of the LP problem, then all John multipliers are normal. Now, as I told you that we had been studying algorithms for unconstant optimization, and while studying algorithms for unconstant optimization, we stopped at a certain point. We stopped after the Newton's method. We said that the Newton's method is sometimes not very helpful, because we do not know whether the Hessian matrix is always positive definite at those points of iteration. So, we cannot really get a descent direction at every xk. So, how can you remedy this situation? To remedy this situation, we needed some modification originally initiated by W.C. Davidan, though there is an ironical story here which we will tell you tomorrow after I give the homework for this part on the KKT part. The ironical What is very fascinating, W.C. Deveron actually invented the method, but his all papers following his actual work was published, and his paper was published possibly the last among all the legendary works in that area. So, what I want to say is that there we remarked that if I want to study the improvements of the Newton methods called the quasi-Newton methods or quasi-Newton methods, as some people would like to say, in that case we need to understand constraint optimization. All these methods have come after all these KKT conditions or Fridtjohn conditions were known. So, we need to use the optimality conditions there, the constraint optimality conditions. Hence, we shifted and reverted back our study and came to Karush-Huntaker conditions or John conditions, whatever you want to call it. Now, once we have done that, we are now going to keep our promise and go back to the quasi-Newton method and show that how these results can be applied to get a very interesting and conclusive theory, and that would generate algorithms which are still very effective, used in softwares, are quite fast, and was considered as one of the revolutions in optimization in the 70s and early 80s. So, before all these other things like interior point methods and conic programming and semi-definite programming taking over. So, what we are going to learn is essentially a revolution in optimization carried out by few great researchers in this subject. So, with this little fact that you have learned today, which is I think a very interesting fact to go through this step by step. Now, I will leave you here with a question. Now, here I could go back and write such a system and do all these things because of the fact that I know the Fridtjohn conditions at the very beginning. Since I know the Fridtjohn conditions, I am writing this story. Okay, that is also true. Now, you can tell me one thing very clearly, that okay, I would also leave you this part, that to write the theorem in a nice way, what we have shown is that if x star is a solution, there would exist a multiplier lambda not equal to 1, lambda bar in Rm, S star in Rn plus. Of course, here we have to note that this has to be in Rn plus, we have written it here. So, we can also add it here, wait, S star greater than equal to 0. So, such that these conditions are satisfied. Now, here because we knew about the Fridtjohn condition, we could gauge this change and make this change here. So, this is one way to go about it. This could be looking slightly artificial to you, because suppose you are just given a linear optimization problem and you do not really know anything about the Karush-Huntaker conditions. How do you deduce an optimality condition? This is the question I am keeping in front of you. You will get this solution in the FAQ, but this is a question I am actually keeping in front of you for you to really ponder. So, with this I will end my talk today. Thank you very much for listening.